In 2022, Germany made massive headlines. They completely shut down their remaining nuclear power plants. But, even with those reactors completely offline, there's still a monumental challenge left behind, safely storing about 27,000 cubic meters of highly radioactive waste. That is a staggering amount of hazardous material just sitting there. But right now, there's this radical new concept emerging. It's a massive engineering leap, and developers are actually claiming it could not only provide totally clean energy, but get this, it could actually use that exact radioactive waste as its fuel. Crazy, right? Okay, let's dive into this. Here's our roadmap for this explainer. First up, we'll look at the German energy dilemma. Second, we'll break down exactly how this dual fluid reactor works. Third, we're going to explore using nuclear waste as clean fuel. And finally, we'll hit on the skepticism, costs, and timeline. Section 1, the German energy dilemma. To really get the hype around these new reactors, we first need to understand exactly why the hunt for reliable, clean power in Germany is so incredibly urgent right now. So, renewable energies, we're talking wind, solar, hydro, biomass, they are doing a fantastic job. They're providing over half of the power mix right now, sitting at 51.5%. On paper, that sounds like a massive win. But here is the paradox. Renewables are notoriously dependent on the weather. And because of that inconsistency, a massive 36.1% of the energy mix still has to rely heavily on dirty fossil fuels like lignite and coal just to keep the lights on and maintain a constant output. Traditional nuclear power, well, that used to make up the remaining 12.4%, offering a steady, reliable stream of power without those nasty CO2 emissions. Now, what's really interesting about this slide is it brings up a fascinating paradox that totally challenges a narrative we hear all the time, the idea that traditional nuclear energy is the cheapest option out there. Look at the numbers. The operating costs for a single kilowatt hour of nuclear power hover right around 13 cents. But then you compare that to solar energy, which ranges from just 3.7 to 11.5 cents. There are even claims floating around that organizations like the International Energy Agency might have intentionally undercalculated nuclear costs in the past just to make them look a bit better. Whether that's true or not, the hard data shows that traditional nuclear energy just isn't the rock-bottom cheap solution that so many people assume it to be. Section 2. How does the dual fluid reactor work? With traditional nuclear power facing these really strict cost and waste issues, how exactly are these developers planning to reinvent the wheel with the dual fluid reactor? Well, for decades, the standard nuclear playbook has relied on solid fuel rods, usually made of uranium, submerged in water, which basically acts as the coolant. The dual fluid reactor completely throws out that entire paradigm, literally. Instead of solid rods and water, it uses two entirely separate liquid cycles. The fuel itself is actually a liquid, either a molten salt or a liquid metal. And the cooling cycle, that uses liquid lead. You might be wondering, why on earth would they use liquid lead? Well, its natural properties in reactor setting are absolutely incredible. It absorbs massive amounts of heat, and it naturally shields against radiation, so it essentially acts as a built-in safety buffer. But here is the most fascinating part of all this. As the liquid lead flows right past that extremely hot radioactive fuel core to absorb the heat, the lead itself does not become radioactive. No way. It stays completely neutral. Because of these highly efficient liquid cycles, the core of this thing can reach a staggering 1,000 degrees Celsius. That is nearly 3 times hotter than conventional reactors. And this immense heat unlocks entirely new applications. Instead of just using it to generate electricity, this 1,000-degree process heat could literally be piped directly into industrial manufacturing. It could power citywide heating grids, or, and this is amazing, it could actually be used to propel massive cargo ships across the ocean, completely replacing highly polluting heavy fuel oils. It's a real game changer. Section 3, nuclear waste as clean fuel. Okay. We now arrive at arguably the most mind-bending claim made by these developers. They want to take the exact problem that has plagued the nuclear industry for decades, the highly dangerous radioactive waste, and actually use it as their primary fuel source. So how exactly does this radical recycling process work? Here's the step-by-step. First, they actually go and retrieve old, highly toxic fuel rods, the ones heavy in plutonium and americium that are just sitting in storage facilities right now. Next, they run them through a specialized processing plant to literally grind them down into a powder. Then, this ground-up toxic waste is mixed directly into that liquid salt or metal base we talked about earlier. Finally, this newly created liquid fuel is pumped right into the reactor, where those long-lived radioactive particles are split apart, generating an immense amount of power. And this brilliantly illustrates the ultimate payoff here, which is honestly hard to overstate. Traditional radioactive waste has a terrifying half-life. We are talking up to 703.8 million years. Let that sink in. But by running this waste through the dual-fluid reactor and splitting those specific long-lived isotopes, developers claim they can slash that radioactive half-life down to just 300 years. That takes a geological storage nightmare and transforms it into a manageable, multi-generational timeframe. Oh, and it produces zero new long-term waste in the process. If you take the developers at their word, and that's a big if, the efficiency metrics are just staggering. They state that the dual-fluid reactor operates at 10 times the efficiency of current traditional nuclear power plants. And on top of that, they claim it is 200 times more efficient than modern wind farms. Because the whole operation is completely climate neutral and actually disposes of legacy nuclear waste, the developers argue this technology is vastly more environmentally friendly than even renewable energies. Section 4. Skepticism, Costs, and Timeline. Look, those are incredible, world-changing promises. But we have to anchor ourselves back in reality for a second. Despite these fantastic claims, this technology is currently just a theory. It exists in blueprints and patent filings, not in the physical world. Let's look at the hurdles actually standing in the way. The developers have mapped out a highly ambitious timeline for bringing this to life. The initial patent was filed way back in 2013. The next major milestone is right around the corner. They want to build a physical test facility by 2026. If that works out, they aim to have a working prototype and a pre-series reactor by 2029, which would then lead to full-scale mass production by 2034. They actually claim that once deployed, this technology could completely decarbonize Germany, bringing its CO2 emissions to absolute zero within just 15 years. But, as you can probably guess, bringing a theoretical nuclear reactor to life requires a staggering amount of capital. Just to get through the development phase, run the feasibility studies, and reach mass production, they estimate it's going to cost about 8.5 billion euros. And then, once they are actually in production, each individual power plant will cost roughly 1.5 billion euros to construct. That means they have to convince investors to risk billions of dollars on a totally unproven concept before a single watt of commercial electricity is ever even generated. So the crucial point is, the broader scientific community is pushing back with some really heavy skepticism. The primary concern? Our fundamental lack of real-world experience with liquid salt reactors on a commercial scale. Because the materials and temperatures are so incredibly extreme, scientists warn that potential complications are basically impossible to predict. And in the realm of nuclear energy, unpredictable is a terrifying word. The catastrophic memories of Chernobyl and Fukushima demand extreme caution when we're talking about deploying any new, unproven nuclear system. This leaves us standing at a really fascinating technological crossroads. On one hand, you have a proposed system that could virtually eliminate carbon emissions, provide endless baseload power, and literally eat our existing nuclear waste. I mean, it sounds like sci-fi. On the other hand, we face multi-billion-dollar costs, immense engineering hurdles, and the inherent risks of deploying unproven, extreme-temperature nuclear tech on a massive scale. So, is this the brilliant climate salvation we've all been waiting for, or just a dangerously expensive distraction from proven renewables? Thank you so much for joining me for this explainer. We'll let you decide.